Now let's do an example of a Zener diode problem. So let's say we have a voltage source connected to a resistor and connected to another resistor. And here we have a Zener diode in the circuit as shown. So this is 10 volts, 100 ohms, 200 ohms, and the Zener diode has a voltage of 6.0 volts. Okay, so let's say we're trying to find the current through this 200 ohm resistor. And if this, if this 200 ohm resistor represents a load on the circuit, we were trying to find the current through the load. Okay, so to figure out what's going on, we want to figure out what the diode is doing before we can really successfully analyze the circuit. So we're going to do what we did with normal diodes. The first thing we're going to do is say, what would happen if the diode were off? Meaning that we could replace this with an open circuit. So if the diode were off, if we replace this with an open circuit, we can redraw the circuit like this. We can leave that there to remind us, but that's, this isn't doing anything in the circuit. So we have 10 volts, 100 ohms, 200 ohms, and this is a simple voltage divider equation. So at this point, our voltage is going to be 200 divided by 300 times 10 volts. So that is 6.67 volts. Okay, so is 6.7 volts here consistent with the diode being off? Well, that would mean there was 6.67 volts here and 0 volts here, which means our diode is reverse biased with a voltage difference of 6.67 volts, which if we go to our graph really quickly, that is somewhere over here, right? Because the Zener diode voltage is minus 6 volts. So we cannot have a voltage like that on our diode. So it is not consistent for the diode to be off, and this has to be wrong. Cannot be off. So now we know there's current flowing in the diode, and just with that is by itself enough to figure out what's going on, because it wouldn't make sense for there to be current flowing this way because this is at a lower voltage than this, no matter what's going on, right? If this is 0, we don't have some voltage lower than 0. So in other words, if we know the diode is on, we know that there must be current flowing this way through the diode, and that's enough to analyze what's going on. If you don't believe me, you can check. You say, okay, well, what happens? What would have to happen for there to be voltage flowing that way through the diode? You would see that the spot would have to be at minus 0.7 volts, and that is not going to make any sense. So I'm going to skip right to the fact that there is current flowing that way through the diode. And we actually don't care about how much right now. What we care about is what this tells us with regard to the voltage. So for the Zener diode to be conducting current in the reverse direction, we know there has to be a 6 volt drop across it. So if this is 0 volts, this point has to be 6 volts. And now we can finish analyzing the rest of the problem. So if this point is 6 volts, this point is 6 volts. And so the current through this is going to be I equals V over R. That is 6 over 200, which is equal to 30 milliamps, 0.03 amps. And that was what we were trying to find. There is current flowing through the Zener diode, and we can see this because here, going through this resistor, we have 10 volts on this side and 6 volts on this side. So that's a 4 volt difference over 100 ohms. So that is 40 milliamps of current through there. So if we have 40, think about this junction. If we have 40 milliamps going into it and 30 milliamps going out that way, through the Zener diode, which I'll draw over here for clarity's sake, we must have 10 milliamps of current flowing through the Zener diode in the reverse direction. Okay, easy. So let's ask a couple other questions. And let's talk about kind of the why of this circuit, because this is not a random useless circuit. So if we were thinking about this 200 ohm resistor as our load, meaning our 200 ohm resistor is connected to this circuit on the left. So this circuit on the left is like a thing that we are connecting this 200 ohm load to. Something neat happens with this Zener diode in this configuration. And that is, if this voltage over here is 10 volts, we see that this load has a voltage of 6 volts because of the Zener diode and a current of 30 milliamps. That was what we just saw. So what happens if our voltage supply here, let's say what happens if it increases, or if it decreases to 9.5 volts? Well, we can go through all the same analysis steps we did before. I'm not going to repeat them because literally they're all the same, except for instead of 6.67, it's going to be 6.5 or 6.4 or something. And that doesn't change anything about what's going on. That is still going to say, oh, the Zener diode has to be conducting current in the reverse direction, and therefore the Zener voltage is 6 volts, and therefore the drop across this is 6 volts, and the current is 30 milliamps. So even though we changed this voltage, what's going on with the load is staying exactly the same. We'll get a different amount of current here. We'll get a different current through the Zener diode, but that's okay. It can probably handle it. Okay, what happens if we change this to 15 volts or something crazy like that? Well, then we do the exact same thing. We say, okay, if the Zener diode is off, we get our voltage divider. That's going to give us 10 volts here. And of course that doesn't work because that would mean the Zener diode isn't off, it's on. So therefore the Zener diode must not be off. So it still must be conducting in the reverse direction. It still must have a 6 volt drop across it. And therefore the load must still be feeling a 6 volt drop and have 30 milliamps of current through it. So the Zener diode here is keeping the voltage across the load the same, kind of no matter what's happening over here. There are limits here. We might at some point flow enough current to damage the Zener diode, or if this is low enough, I think in this case below 9 volts, this point is going to have to be below 6 volts and the Zener diode is going to turn off. But outside of those limits, these numbers are going to, within those limits, these numbers are going to stay the same. So this is called a voltage regulator. And this is kind of the simplest two-component voltage regulator. And this is it's able to perform this function for different values of the load too. There are lots of other resistances besides 200 ohms that would still feel this 6 volts of voltage and have whatever their corresponding amount of current is at 6 volts. Voltage regulators are very, very important in practical electronics. Generally, we're not designing them. Voltage regulators in real life tend to be circuits that you kind of buy already completed and add as components to your circuit. But it's important to understand how they work, and this is one simple form of a voltage regulator.